Hi there, my name is Aaron Lanterman, and I'm a professor of electrical and computer engineering at Georgia Tech, and this is my quarantine hair. And I would like to welcome you to the first lecture of ECE3084 Signals and Systems in the summer 2020 semester. Normally I would be giving these lectures before a live audience at Georgia Tech, but COVID-19 had different plans, so I will be recording my lectures this semester and posting them on YouTube in the hopes that other people will find them useful. The subject of signals and systems forms the basis of digital signal processing, image processing and pattern recognition, communication systems, both wired and wireless, the design of feedback control systems, radar systems, including systems that form images and track multiple targets. It's also an important part of circuit design. It's also fundamental to understanding music and audio in general, and its tools can be used to understand both electronic and acoustic instruments. Okay, so this is allegedly a class on signals and systems. So what do we mean by signals? I'll try going Khan Academy style here with a black background. So we're going to think about these signals as just functions. So we'll commonly have some function of time. So we could imagine that this is mapping some real numbers to some real numbers, where we're mapping time measured perhaps in seconds or perhaps in years or perhaps in nanoseconds to some other value. And maybe this is pressure, sound pressure for sound waves representing my voice. Maybe it's representing a voltage or a current in an electrical system. Maybe it's representing some sort of measure of the intensity of light, whatever it might be. Or you might have some two-dimensional function. Here I might write that as f, x and y, where x and y are positions. So here I'm mapping maybe a couple of real variables to some other real variable, and very commonly this is representing something like light for an image. When I went to the two-dimensional function, because I wanted to use x and y to represent coordinates, I couldn't use x as a function name as I was previously, so maybe here, if this was more of an image processing course, I might use a function like f. Now, perhaps this is a color image, so I would probably have some red, I would also have some green, I would also have some blue, if it was an RGB kind of image, in which case I might put a cube on this. You might have some sort of image that's a function of time, and that would be representative of a movie. Or you might have some sort of image that is actually some sort of three-dimensional volume, like maybe a volumetric magnetic resonance image scan. Or maybe that kind of scan is being taken over time, in which case you might have a three-dimensional quote-unquote image that also itself is a function of t. And I used to teach a class in ECE called ECE6279, which was array signal processing, that was kind of like this class, except looking specifically at these four-dimensional functions, and specifically looking at functions that satisfy the wave equation to build algorithms that deal with such four-dimensional data, taking advantage of that structure. So there may be some ambiguity about what we mean by the term signal. Here I'm writing a signal in the general sense that may represent a signal in a very specific sense, in that there may be some information that we're looking for, say in a communication system. So there may be something in the signal that embeds a message that I'm trying to send. But I have to send this over some sort of noisy medium, and maybe I'll have another signal in the general sense represented by this W that here represents noise. And I add these two together to maybe get something I'll call here R of t, which is the signal in the general sense that I actually receive. So here I have a signal in the general sense, a signal in the general sense, and here I have a signal in the general sense, but also in the very specific sense of containing a piece of information that we're looking for. Generally, this course will mean the term signal to be something fairly general. Okay, so if that's what we mean by signals, what do we mean by systems? So in this course, we're generally going to think about systems as things that map signals, say x of t here, onto other signals, say y of t. Now, our happy system here may be something that models a physical phenomena in the universe. Maybe it's representing the effects of trying to take a signal and transmit it through some sort of complicated mountainous region where there's all kinds of multipath signals bouncing around here. This can create problems for something like a cell phone communication system. Or maybe it's some sort of circuit you've built inside of your cell phone that takes the information from the antenna. So imagine this is an old school cell phone that actually has an external antenna for a second, and tries to remove some signals that are generally interference of some kind. So here we have something that is mapping functions to other functions. So you could think of our system here, maybe we represent it with this giant fancy S, as taking some signal here that's mapping, say, time to voltage, and that's turning it into another function that's mapping time to some sort of voltage. Say this represents an electrical circuit of some kind. Say you put a resistor here and a capacitor here, and you drove this with some sort of input voltage and you measured an output voltage. So this level of formalism of having a function that maps a function that maps real numbers to a function that's mapping real numbers to real numbers, this is way more fancy than what we need to do in most of the course, so we generally won't bother writing out things like this. Something hiding in the background here that we'll come back to is maybe this is not actually an analog circuit made of resistors and capacitors. Maybe there's some sort of discrete time system in here that's taking a signal from an analog digital converter and taking its output through a digital to analog converter that's trying to pretend to be something like this. So this is the main subject of a class at Georgia Tech called 2026, which I'll come back to, and we will address later in the course. So as a bit of a preview, in the next lecture, we're going to talk about a few very specific special signals that will give us a lot of leverage in thinking about signals and systems. One of them is called the Dirac delta function, and the other is called the unit step function. We're also going to spend some time looking at system properties, because if there's certain properties that systems have, there's a large battery of techniques that we can bring into play. So imagine we have a generic system here. It's happy, but it's not as happy as it can be. Or more to the point, we're not as happy as we can be. If it has a property called linearity, if our system is linear, then we make that a really big smile. And if it also has the property of being time invariant, we're extra happy because then we can put on the top hat of time invariance. And if we have both of these properties, if a system is both linear and time invariant, we'll call it an LTI system, then there's a whole lot of fun that can come from this. There's a large battery of techniques that came out of the work of the mathematician Fourier. He's dead, by the way. And then later in the course, we'll utilize techniques by the mathematician Laplace, who incidentally is also dead. So let's talk a little bit about mathematics. Mathematics is a language. It's also a way of thinking. The level of mathematics you need to be successful at this course, and for that matter, most of electrical engineering, is not actually that super fancy. So you do need to know some calculus. You need to be able to integrate e to the t dt, exponential functions. You need to be able to integrate cosine of t dt. You need to be able to integrate sine of t dt, and also, of course, take these derivatives. There's one place in the course where I integrate by parts, but other than that, I try to avoid integrating by parts. So you do need to have some familiarity with differential equations, but not much really. Maybe the first month or so of a typical differential equations class. I just made up that month figure. I haven't actually looked at a syllabus for differential equations in a while, because we'll pretty much be sticking to linear equations with constant coefficients that represent a relatively small battery of techniques compared to all of the things that you look at in a typical differential equations class. Now, electrical engineering does have some scary math in it at the undergraduate level, particularly the 3D vector calculus you need in order to do electromagnetics, but we're not going to get into this, which is a good thing because this scares me very much. So let's fade to white and talk a little bit about the history of the course and its prerequisite structure. So in the early 1990s, two of my colleagues thought to themselves, how can we better teach students in electrical engineering? One of them was Ron Schaefer, who largely invented digital signal processing along with his advisor Alan Oppenheim, and the other was Jim McClellan, who among other things has his own transform called the McClellan transform that's built into MATLAB, just like with Fourier transforms and Laplace transforms. Fortunately, Jim is very much still alive. Oftentimes, professors at this level try to get out of teaching students, and at least definitely try to get out of teaching undergrads, and at least definitely try to get out of teaching sophomores. But they thought, how can we better educate sophomores? They noticed that although technology had changed a great deal from, say, the 1960s to the 1990s, and they noticed that the kind of applications that might motivate young students evolved along with it, the way introductory electrical engineering was taught had changed barely at all. The focus was still on classes with circuits containing resistors, capacitors, and inductors. But now, not only were there fast computers that could run digital signal processing algorithms, there were tools such as MATLAB that could allow students to write digital signal processing algorithms and run them without having to mess with the horrors of something like Fortran. So it came to pass that along with their colleague Mark Yoder from Rose-Hulman, they created this curriculum and textbook called DSP First. And I read this cover to cover when I first joined Georgia Tech as a brand new assistant professor in 2001. And when Jim McClellan told me that they teach digital signal processing to sophomores, that sounded kind of insane to me. I thought, how could you possibly teach discrete time system theory before teaching continuous time system theory? But the more I got into teaching this particular material, this particular way, I was sold on the benefits of the approach. So in a weird twist of fate, Georgia Tech switched from the quarter system to the semester system right after DSP First was published. So they wound up creating a course called ECE3084 under the new semester system, and this was the course that I taught recitations for the first semester I joined Georgia Tech, where the original DSP First curriculum took up about 2/3 of the semester, and then the last third was a new set of material that dealt with continuous time topics, such as the continuous time Fourier transform and continuous time convolution. And I taught this material off and on in different ways, either as a recitation professor or as a lecturer and administrator for about a decade. And then in 2010, EC made a major curriculum revision. So something I always observed about 2025 is that we would often lose students through this transition. The first part of DSP First had a lot of lab assignments on the computer, and while they developed some nice GUIs for exploring continuous time systems, for the most part the labs and the material diverged at this point. Some students had difficulty with the slightly more esoteric nature of some of the material in the continuous time domain, and we'll talk about this later, such as going from the discrete time delta function to the continuous time delta function. The continuous time delta function has a lot of weirdness associated with it. I think at this point, students were just tired. This was a very packed 4-credit-hour class that was kind of a bit of a juggernaut. So when we did the 2010 revision, we split this into 2 courses. So there is a new EC3086, which was basically the original DSP First again, that first 2/3 of the semester, plus some material on the discrete time Fourier transform and the poorly named discrete Fourier transform. And this material on continuous time signals and systems formed the first third or so of this new course that we're talking about called ECE3084. And we added to it material on the Laplace transform, including applications such as design of proportional integral derivative PID controllers. So 3084 is really the second course in a 2-course sequence with EC2026 forming a prerequisite. I will often make references to material from 2026, That said, if you're out there in the wild, not a Georgia Tech student, and obviously then hadn't taken 2026, you'll still be able to follow most of the discussion in 3084. To a large extent, 3084 parallels the structure of 2026. 2026 talks about discrete time convolution. 3084 will talk about continuous time convolution. 2026 talked about the discrete time Fourier transform. 3084 will talk about the continuous time Fourier transform. 2026 talked about the Z transform. 3084 will talk about the Laplace transform. We will also make connections to these, particularly in the areas of relating Laplace transforms to Z transforms. And 2026 and 3084 both deal with the concept of sampling and aliasing. In 2026, we pretty much restrict the discussion of sampling to talking about sinusoids, but 3084 will be able to revisit from a more sophisticated standpoint using the tools of the continuous time Fourier transform. So 3084 actually has a second prerequisite branch feeding it. The first we just talked about, ECE3086, is these various concepts we'll look at in 3084, but where they were first introduced in the discrete time context. And if you're a student who did not like 2026, sorry, 3084 is largely 2026 again with the concepts in continuous time instead of discrete time. That said, there is some advantage to seeing concepts twice. And I've had a lot of students in 3084 tell me that seeing it again in 3084 helped them either understand something they originally didn't understand in 26 or help solidify and make connections they didn't have before. The second branch is linear circuit theory. So here I'm talking about resistors, capacitors, inductors, and these neat little nifty devices called operational amplifiers, dealt with in an ideal sort of way. At Georgia Tech, if you're an ECE student, you get this from ECE2040. If you're a Bachelor of Science in Music Technology student doing the electrical engineering concentration I designed, we have a path where you can get this material from ECE3710, which is the primary double E course for non-double E majors. It works here. It'll work fine here. Now, if you're out in the wild and just watching these lectures and don't know anything about circuit theory, well, you'll still enjoy most of 3084. Other than a few examples here and there, this is mostly confined to a section where we talk about using Laplace transforms to help with circuit analysis, particularly in circuits that have complicated initial conditions. So I would also like to show you a website that I created, ec3084.ec.gotech.edu, that's useful not just for students taking my particular version of 3084, but any student taking 3084 in any section by any other professor, and also just for people out there in the world, other students taking signals and systems courses at other universities of various sorts, or just folks out there interested in this material. The template provided by Georgia Tech, come to think of it, isn't super clear. There's a home button, which is apparently broke. I should fix that. Anyway, I have links here to videos that other professors have put onto YouTube or other sites, including other 3084 instructors like Matthew Block, Tim Brothers, Franco Fedele, a few old videos by myself that I'll replace with newer, fancier versions. I also have a lot of videos from other places, in particular the MIT versions of this course. I've done some curating and rearranging to try to put the material in the order that we teach it in 3084, which doesn't exactly line up with MIT's version. There's also a set of notes here by various folks, in particular by Brendan Carroll, who taught at Georgia Tech Lorraine. His notes are based very heavily on notes by Professor Jennifer Michaels that I largely created the bulk of this course with from 2013 to the time that she retired. And so these are pretty nice. You could probably actually read these notes and not even watch my lectures. I have links to a few websites. As a historical interest, the first time I taught this class was in fall 2012. That's actually the first time anyone taught it, and Magnus Egerstedt, who's now my boss, and I did the first version of this class. It's changed a lot since that initial run. And there's also John Barry's site here. And when he teaches it, he likes to use PowerPoint slides, so you can check those out as well. I'm mostly going to be working off of this quote-unquote blackboard in the Khan Academy style, just because I never got around to making slides for most of this course. And I've also found sometimes for mathematical things, I tend to go a little too fast if I have PowerPoint, and having to write things on a board forces me to slow down. Okay, let's fade back to black and do a little preview of next lecture. The next lecture is going to focus on a couple of very useful signals. One is going to be the unit step function. One is going to be the very strange generalized function. It's not really a function, called the Dirac delta function that does all sorts of weird, cool, useful stuff. And we'll talk about how to do naughty things that your calculus professor would probably disapprove of, like take the derivative of discontinuous functions and talk about how that could possibly hand-wavily make some kind of sense.